Thank you for the nice introduction. So, good evening. So, the title of my presentation is, Should You Trust an Autonomous Vehicle? And hopefully by the end of my presentation, you will realize that you should not trust an autonomous vehicle. And the reason for that is, okay, let's see what is the bottleneck in deploying autonomous vehicle, right? So, unfortunately, ensuring safety through perception and prediction posed a great challenge in deploying autonomous car. So let's look at this example. Let's say there is a child is, biking, going to a street, and there is a car approaching. So what are the sensors on the autonomous car? So we have cameras, we have LiDAR, we have radar, right? So they actually get all these inputs from the environment. So what is their main role? So their main role is to actually reconstruct the model of the environment, right? So, and the question is, how do we construct this computer's model of the world which is around the vehicle, right? So we are using machine learning techniques, namely deep neural network, to actually construct this huge network which gets all these inputs from video, from radar, from LiDAR, and it tries to construct the world around the vehicle. For example, it says, okay, child is riding a bike 10 meters ahead, entering the street, right? So, of course, the car has to decide based on the action of the child which is biking. So, and of course, the model goes inside different layer, which is called path planning and motion planning, right? So now the car has to navigate in the environment. Of course, it should prevent colliding with the, kids on the bike. And of course, it has to respect traffic light and traffic rules. So you see this part, which I call it perception, this is totally led by machine learning techniques. My own research actually lies here on the path planning and motion planning. And so the good news is we can actually provide formal guarantee. We can provide mathematical guarantee that the motion planning and the path planning is correct as long as the computer's model is correct. So that's the assumption, right? So, okay, what can go wrong? So unfortunately, this model is built completely based on scene data. The data that the car has been observed so far, so they train this, and this is the problem that we are actually facing. So let me actually dive into this more. So machine learning techniques, they do very good in patterns that they has encountered so far. They do great. But the problem is about those scenarios that they have not encountered. And guess what? There are tons of novelty in the world. I mean, you go to different countries, you see things that you haven't seen in your life, right? And in fact, 10 years from now, you're going to see things which you never thought you're going to see in your life. So let me actually ask this question. I put a picture here, and raise your hand if you think that picture represents a chicken. So raise your hand if you think it's a chicken. So now let's put this picture in one of the state-of-the-art image processing algorithm, which is behind the perception engine in the autonomous vehicle, which they are supposed to build the world around the vehicle. And the answer is 99% this is not a person. And this is the problem we are facing. And this is the main reason we cannot deploy self-driving car. So, and these are called edge cases, right? Or corner cases. So these are unforeseen surprises. So these ones surface actually during the testing, and this is the problem. So let's say your self-driving car is able to actually do well in 98% or even 99% of scenario. Is that 1% really the bottleneck? And the answer is yes. So if you want to deploy self-driving car, the guarantee you should provide is in the order of 0.109 after that. Then you are ready to say, okay, I'm actually ready to deploy a self-driving car. And these edge cases are the scenario that you did not even think about it when you were designing your self-driving car. So, of course, the challenge lies in covering everything. Here, a police officer decided to wear a chicken costume. Or are you able to design a self-driving car who's able to actually detect, the holes in the road, right? So maybe as a human, we have some insight, right? Or here, as you can see, there is a reflection of another car in the truck, which is actually driving in front of you. And also, your self-driving car should be compatible and should be, able to navigate in a very complex traffic situation in different countries. So here you can see this magic roundabout, right? So, and of course, it should be able to understand, for example, here, there is a person. Is this person standing next to the bike, or is this person is biking? And you might say, does this matter? Of course it matters. Why is that? Because if the person is biking, you have to predict the speed of the person, right? If it's a standing, so then, these are totally two different assumptions. And that's going to affect on the deployment of the self-driving car and the navigation. So, okay, what is the current practice? Public road testing, right? If you go to San Francisco, you've seen a lot of them, right? What is the pros of them? Of course, they're very efficient in identifying straightforward cases, right? And most of them has been driven in sunny sky. Arizona, Las Vegas, San Francisco, right? And you know why. So what is the con? So first of all, they're very costly. So this is a self-driving car company in China. They're actually trying to test on a designated lane, right? And they can, at the same time, they can be dangerous. So this is the Uber car crash happened in Arizona, 2018. A pedestrian died. And after this incident, Uber actually shut down the whole autonomy division. So one incident, they shut it down, right? So because it affected on people's perception. So, and I'm going to tell you, brute force road testing doesn't work. And the reason for that is, so let's look at the statistic we have. We have one fatal crash for every 100 millions of miles in the US. That includes drunk driver, right? One fatal crash in every 100 million miles. Okay, so let's say we're going to get the better statistical guarantee. So let's say we test at a rate of 3 to 10 times longer than this, one fatal crash per 100 million mile. So that requires approximately 1 billion miles of testing, which means 25 round trips on every paved road in the world. That's the amount of testing you have to do. And you're only allowed to have at most 10 fatal crash. This is not the end of a story. Guess what? You update your software. You update the geometry of your car. It's a sedan, become a SUV. You change the sensor camera. You have to repeat the test from scratch. The result of the previous test does not carry over if you do some changes in your system. So you see, brute force testing is not practical. So the good news is industry is actually working on some standards for autonomous driving or autonomous vehicle. So these are some of them on functional safety, which existed 10 years already. And there's a new one actually developed in European Union, which is called SOTIF, Safety of Intended Functionality, which tries to iteratively mitigate discovered unknowns. So, of course, additionally, we also need to have a list of, did you think about that, right? These are the unknowns that we have to think about it, the corner cases, the edge cases, which might happen in reality, and we have not thought about them, right? So we need to actually continuously enhance based on the lesson learned, and also, we need to have feedback from the unexpected scenario which might happen. So, and this actually happened in Pittsburgh, right? This is a bus. And so in this case, the driver was actually, in real time, he decided the best option is I let the passenger go out of the bus. So now imagine it was a self-driving bus. So, okay, what is the journey to autonomous vehicle safety? We need to actually change the culture within the industry. And we need to provide safety during on-road testing. For example, the incident happened with the Uber crash. So they shut down the whole division, right? So if we cannot provide safety during testing, so that actually is going to impact and it's going to delay the whole process for several years. So we need to actually evolve beyond a rush demo mentality, which is the case now in US. So European a little bit, they are more on the conservative mindset. They're taking their time, they're following the standard. But this demo mindset, which also makes sense because they need to secure the next phase of funding, right? They need to deploy something. So we need to also build stakeholder trust for acceptable safety. For example, as you recall, I said we are using machine learning techniques for the perception. So we need to actually have system level safety for that. And we need to also have our own independent safety assessment for self-driving car. Many actually industry, they do have independent safety assessment. FAA, petroleum industry, many industry. Car industry, actually one of the few which we do not have independent safety assessment. So we need to also leverage industry safety standards. We need to revise regulation and maybe make them mandatory, right? So it's very strange to hear that actually many of the self-driving car companies in the US, they are fighting hard to not have any standard for autonomous vehicle. So, and of course, we need to employ traditional software safety, enhanced with addressing, of course, the unknown unknowns during the deployment regarding those corner cases which might happen. So, yeah, this is the end of my presentation. And I wanted to thank the funding agency in the US, in the European Union, as well as in Germany for helping my research. Thank you.